Okay, how are we going to understand structure constants? What are these things, and why are they stopping us from moving on? Because we have to understand structure constants. So here's our Lie algebra, G. Notice I'm not going to bother with the rest of the fundamental group or the group or anything. We're talking now just inside the Lie algebra. But it does have a basis, which I will list here. Now it's funny, the basis, there's eta generators for the basis. This is where you do kind of need to remember that there's a group out there that's parameterized with eta parameters. But I'm assuming we've covered that. That's sort of what that review was for. We call these the generators of the Lie group, but the real language, I think, is any element of the Lie algebra is a generator of some element of the Lie group because it creates this infinitesimal member of the Lie group, right? So any element of the algebra can go there and generate a member of the Lie, Lie group, and you can exponentiate any member of the Lie algebra to get an arbitrary member of the Lie group, right? Where now we're thinking of this in terms of matrices, and we're always thinking now in terms of matrices. So the word generator out there, as you study the subject, gets a little bit confused. There's the generators, which are the basis vectors of the Lie algebra. Those are sometimes called the generators. But then again, any element of the Lie algebra is the generator of some transformation of the Lie group. These are generators of Lie group movements just right along where only one parameter is changing. These are generators of Lie group elements that are moving in a direction through the Lie group where many parameters are changing at once, but they're equivalent. And yes, you can change the basis. This is just one set of independent matrices that do this. You can change the basis, and in fact, that's a really important thing that we're going to do later, is find a really good basis to make sense of the structure of this stuff. Anyway, so the point is I can take any two elements and I can create this bilinear product of the two, which we'll just write as the commutator. And I don't want to call it, I'm going to call it the bracket. Mathematicians like to call it the bracket because the commutator is a thing about group, right? Remember, the commutator was what's that little line on my B doing there? A, B, A inverse, B inverse. That was the commutator. And that's something that's a group thing, right? But remember, this is an algebra. So calling this the commutator is very physicsy, but mathematicians will call it the bracket. So let's play mathematician. We'll call it the bracket. And as we kind of droned on and on about, this is going to be equal to some element inside the group W. So let's focus on this. Y, Z equals W. Well, it totally stands to reason, right, that W is expressible in the basis, say Wi, Xi, right? So W has an expansion in the basis. So do these guys, by the way. These guys have expansions in the basis. So let's break everything out. Yi, Xi, Z, oops. I guess I want sort of a scripty Z. Zi, Xi equals Wi, Xi, like that. So now on the left side, I can take out the Y and Z, right? Y, well, shoot. I need to, not everything can be I, right? They're all dummy indices, so in some sense they can be. But let me do J here and J here and K here and K here, right? So Yi, Z, J, Xi, Xj equals W, K, X, K. So the point of this is, as usual, G is a vector space. Every element of a vector space can be expressed as in terms of the basis, right? That's the whole point of a basis. So the point I'm trying to make is an arbitrary bracket between arbitrary vectors can be understood as the components of those vectors in the basis you've chosen, in our basis, multiplied by the bracket of just the basis elements. So if you understand the bracket of just the basis elements, you can then find the bracket of any elements, right? As long as you know how those elements are expressed in terms of the basis. So we need to know these guys, right? We need to know these guys. Well, so that's not a problem because these guys here, right? Let's just break that out. xi, xj has got to equal sum over x. Well, let's go back with k, right? Well, what's that sum going to be? Well, it's going to be some number that sums over k, right? It's going to be some set of variables that sum over k. But we can name those variables by the I and the j that matter, right? So Cij like that, summing over k. And this is written various ways, right? Ckij xk, where that actually has this sort of tensor structure where we leave a space there. But it's also very often written Cij kxk, where they want to emphasize that, look, this is where the sum is. This is the name of the thing. But it's still got this tensor structure because there's a space here. This one doesn't have the tensor structure at all because everything's right up on down on top of each other. It turns out the tensor structure is justified. For those of you who remember the What is a Tensor lecture, these guys actually transform under a transformation of the vector space like a tensor. So this would be our official way of writing a tensor, and we would have called that a 1-2 tensor. This guy, it's not technically a quote-unquote tensor in our semantic system because you've got these covariant indices first and the contravariant indices second, right? So we can't, with our rank structure, the contravariant indices come first and the covariant indices come second. However, as I kind of pointed out in those lectures, that's totally a semantic matter of what we want to call a tensor. They're all multilinear maps that behave exactly the same way, and if you understand it, you understand it. It's just in order for us to give these guys a rank name. The point is we don't have to worry about any of that right now. The fact that this transforms as a tensor is not something we deal with or need to deal with at all in our work. We just need to understand the sum structure, the Einstein sum structure. So this is actually my favorite way of doing it because this says the Cij, which tells us, the two basis elements being commuted or being bracketed, and the sum over k. So we need to know what these numbers are. And if we know what these numbers are, then we know all of the brackets for the basis elements. And if we know all the brackets for the basis elements, we know all the brackets for every element, right? So these guys here are called the structure constants. There you go, the structure constants. And the structure constants, you've heard this before, tell us everything we need to know about the algebra. Well, okay, kind of obvious, right? The algebra is defined by the bracket. Well, the bracket is defined by how it operates on the basis, and the structure constants tell us how it operates on the basis. So that's what that means. The structure constants tell us everything we need to know about the algebra. So the structure constants shouldn't really be much of a mystery here. I guess we should flush out this line here, right? So we did an aside to analyze this. So now let's kind of finish this up, right? We have I and J. So we know what this guy is. So let's now make the substitution. And that substitution looks like this, right? This guy here, that's supposed to be a Z, not an eta. But yi zj, now this gets replaced by cijk xk. So this wk, which this is your arbitrary, or not arbitrary, this is your resulting vector from this bracket operation, the resulting vector. Well, this is how you calculate WK, the resulting vector's components in the basis, in this basis here, right? In this basis here, the resulting vector's components, WK, this is equal to this guy right here. And you'll see, everything sums out. The J sums and the I sums, so there's only a K, and there it is. So that's why the structure constants are so important, as it allows you to calculate this bracket for any two elements. All right, so is there anything else to say before we do an example? I think maybe not. Of course, pulling out these guys from in here, this is a bilinear mapping, right? That's the whole point is, x, y minus y, x, if I have alpha x, y, alpha x, beta y, beta y, alpha x, where that's some real number, obviously you can make it alpha, beta, x, y, right? So the bilinearity is an important feature here. Okay, so what we'll do is we will do an example where we will begin with a Lie algebra, and not the Lie group. We'll just begin with a Lie algebra or proposed Lie algebra, and we'll calculate all of these structure constants. So let's do that. All right, so let us think about these four matrices. I made them big and bold because you might as well memorize them now if you don't already know them. They're called the Pauli spin matrices. Now, we're not going to worry about, we're thinking about this mathematically, right? I'm not going to go right into the physics that might drop out these matrices. That is for a different subject. But if you've done any quantum mechanics, you've definitely seen these guys. And we are going to use them as the basis for our Lie algebra, right? Our Lie algebra is going to have a basis of small sigma I. And we're not deriving this from a group, right? I'm just starting with the algebra, right? That's what we're going to do in this case. We're going to start with the algebra. And this is actually motivated through our group work. I'll do that at the end to show you how we might have derived these. But let's just say that there is a Lie algebra out there where these guys are the basis vectors. Now, we could formally check, right? Without knowing the group, we could check to see if these guys here do form the basis of a Lie algebra. And what we would do to check is, one, is we would check for closure under the bracket operation, right? We would check sigma I, sigma j, right, equals c I j k sigma undo sigma k, right? We definitely check to see if it's closed. That would be important. If the basis is closed, then we know the entire algebra will be closed. So that's important. And then the other thing we would need to check is we would need to check the Jacobi identity. So the Jacobi identity would start, I would write sigma I, the bracket between sigma I and the resulting vector from the bracket of j and k, and then I cyclically permute these, right? So then, and add them all together. So this becomes j, k, I, and then this becomes k, I, j, right? And that all, when you add them up, needs to equal 0. Now, we haven't discussed this, but I want to get into some examples of working with the Lie algebra, and I want to start with a Lie algebra. So I'm starting with these four things. Turns out the formal definition of a Lie algebra is this: the vector space formed by these guys is easy. It's going to be a complex vector space, right? We're going to deal with a complex vector space. So any complex number, alphas a0 plus a1 plus a2 times this plus a3 times that, that will be a matrix, a 2x2 matrix. That will be considered inside the algebra. So we know we're going to be close. I mean, we can make a vector space. These guys are linearly independent in the sense that every matrix we deal with is going to be a sum of these four, and none of these, you can't you can't make sigma 1 out of sigma 0, 2, and 3, and likewise with all the others. So they're linearly independent, and all of those guys, and we're going to show, so we're going to study this a little bit, and we're going to work on the closure. But then once you get closure, you've also got to prove that it satisfies this. And that's a little more complicated condition, which we'll talk about later. But it can be shown, and we will show it maybe. But the point is this is going to be our Lie algebra that we're going to work with. And I've described it completely. I've described its basis, and I said it's complex, so I've described its coefficients. Since the bracket operation is pretty well understood, we can calculate these, and we'll see that it's going to be closed. And let's give it a shot. All right, so let's see if we can start calculating the structure constants for our Lie algebra, our proposed Lie algebra, I guess. And we'll begin with this one, sigma 0, sigma 1. Well, sigma 0 is this 2 by 2 identity matrix, and sigma 1 is this sort of counter, I don't want to say counter identity because it's not an identity, but it's this, what do they call it? The minor diagonal is unity. And we subtract the opposite form. We're going to do matrix multiplication and matrix addition. Notice this is not the vector addition property, right? Because we don't know that this or this independently will be a matrix inside the algebra, because matrix multiplication is not described in the algebra. The only thing that's in the algebra is this bracket operation. Matrix multiplication exists in the group, but not the algebra. So this subtraction is not guaranteed to take a vector minus a vector. So this is just matrix subtraction. But anyway, this is pretty obvious because this is the identity and this is the identity. So you're just going to get that matrix minus that matrix. Yeah, so it's going to be 0, right? So this guy equals 0. And in fact, it's pretty obvious that this is going to be 0 for everything because it's always going to be the identity times something. So I can go sigma 0, sigma j equals 0. So what does that tell me? That tells me that C 0 j k equals 0. Right? So all C0 AK equals 0. Well, that was fast. Let's do a little trickier one. Okay, let's look at this guy. Notice these matrices have complex entries in it. That is not the same as this. The fact that the scalars are complex numbers does not mean one way or another whether these guys have to have complex entries, right? This is just a matrix. Obviously, these are matrices of complex numbers, clearly. That has to be the case. But you could have a real vector space with complex matrices if you wanted to, right? In other words, this could be a real vector space if you restricted these to the real numbers. That's just a reminder of the meaning of these things. These things are slightly different than you might imagine if you think loosely about it. The fact that it's a complex vector space has to do with the bin of scalars that these scalars are drawn from. It doesn't have to do necessarily with the nature of these matrices that we're choosing, which is the basis of our vector space. Anyway, keep that in mind. So now I can multiply this out. Let me do that. Let's see if I did this correctly. Then I get I minus I, which is 2i and, minus 2i. I did not do it correctly. Minus 2i. And what does that end up equaling? Well, that equals 2 times I, 0, 0, minus I, right? And if I go back here, what do I see? I see this, sigma 3, right? See sigma 3, minus 1, 1, minus 1. Well, that would mean if I pulled out a 2, undo. I could also write that as 2i, 1, 0, 0, minus 1, which equals 2i sigma 3. Well, that tells me that the structure constant 1, 2, 3 equals 2i. And I also know that C1, 2, 0 equals C1, 2, 1 equals C1, 2, 2 equals 0, because there's only one of these matrices that survive the sum. So I've calculated 4, 5, 6, 7, 8 of these guys already. So that's cool. I'll just put the summary right here, 2i sigma 3. Okay, so let's do another one. Oh, wait. I should point out, obviously, it should not be hard to see that sigma 2, sigma 1, right, is going to equal minus 2i sigma 3, right? So I've also calculated the fact that these guys are, the bracket operation is antisymmetric, means I've also calculated C2, 1, 0 equals C2, 1, 1 equals C2, 1, C2, 1, 2 equals 0, right? These guys are all equal to 0. Yeah, equals 0 like that. And C2, 1, 3 equals minus C1, 2, 3, which equals minus 2i. So I've done a lot of calculations here. Actually, getting a little bundled up here more than I need to. Okay, so the point is we calculate these things at a pretty poppy rate here, especially the reason we calculate so many so quickly is that this rule, this bracket operation, was quite simple. Only one of our generators was relevant in the bracket of two of the other generators, and that pattern is going to continue. All right, so we're working on sigma 1, 3. I think I've put these incorrectly. It's the minor diagonal and then the major diagonal with a minus 1. Let me make sure I got that right. The minor diagonal and the major diagonal with minus 1. Okay, so let's calculate those. Okay, I think I got this one worked out. The product of these two matrices is this minor diagonal with a minus 1. It's going to be the same thing, actually just opposite in sign. We subtract them, it kind of doubles up. So we see this 2 showing up again. We pull out the 2 and we get this 1 minus 1. And then you go back here and you say, oh, gee, 1 minus 1 is not here, but sigma 2 is minus I. All right, close enough. So we pull out an I. We pull out a negative I. Let's see if I got this right. So I times I is minus 1 times minus 1 is 1 plus a minus 1 here. So that, not plus, but times a minus 1 here, and ends up with a minus 2. And then minus I minus 1 times minus 1 is 2 times 2. So this is the second Pauli spin mate, or sigma sub 2. So this is the guy here, and therefore we now know that C1, 3, 2 equals minus 2i, and C3, 1, 2 equals 2i, and then of course we know that C 1, 3, 0 equals C1, 3, 1 equals C1, 3, 3 equals 0, and so does C3, 1, 0 equals C3, 1, 1 equals C3, 1, 3 equals 0. Okay, so that was good. So we got all those guys down. Let's now do, I guess what's left? 2, 3 is left. 2, 3. We don't have to do 1, 3 because of our inferences about the antisymmetry of this guy, right? In other words, sigma 3 comma sigma 1, the bracket with sigma 3 here, well, the bracket with sigma 3 here and sigma 1 there, right? That bracket is just going to equal the opposite of this, right? Okay, so let's do the last one. Okay, so here I think I've worked it out. As usual, we substitute our matrix for sigma 2 and sigma 3 here. We get the same subtraction of matrices that happen to have opposite signs, which, by the way, none of this is a guaranteed pattern. This is all unique to the sigma matrices. The fact that you end up with a difference that doubles, that's what makes this algebra special, right? That's ultimately what this collection of structure constants does for us. There's nothing here that should be interpreted as general rule for all the algebras. The only thing that's general is the way you calculate it, right? You take two matrices, find their difference, end up with a matrix, and then I take that matrix and I take its decomposition in terms of the basis matrices, and in this case, it just so happens that that decomposition just ends up being a complex number times one of the basis generators, right? It doesn't have to be. This could be plus 2, 3. It could be actually kind of hard. I could get to this spot and be scratching my head. All right, how am I going to break this thing down? What if I had a Lie group that had like 100 basis vectors, right? I don't know. I'm just thinking, and you end up with some matrix here that you have to now decompose into 100 basis vector, right? I mean, it can be done, of course, but I'm just saying that here it's trivial. It's not a problem, but that's one of the reasons we're choosing this group. Also, this group is really, really important in physics and as examples for this, so this is fine. I mean, I'm happy to use a simple system. Believe me, I don't want to. Even this was kind of burdensome for me. Got to remember, the row times the column and all that crap. Okay, anyway, so here, 2i sigma 1. This tells me this structure constant, it's the opposite of that structure constant where the two down indices are switched. All these other guys are 0. So now I know everything, right? Let's sum it all up. All right, so the first thing to sum up is that we know that all of the structure constants related to the sigma 0 element were all equal to 0. All right, so I've written them all down here. And what we have to also understand is they're opposites, right? So if I took 3, 0, and so I'm only going to do half of them because we'll know what the opposites are. But all of these and the transpose of the bottom two are all equal to 0. So that's done. So let's take those and put them aside for a moment. Let's say put them over there. And now let's look at the rest. So we derived these two from the commutator of sigma 1, sigma 2, which equals the opposite of the bracket of C2 sigma 1. So we got these two guys. So let's take them and put them aside. Then we develop this from the commutator. I keep saying commutator. I want to say bracket. I want to train myself to say bracket of sigma 1, sigma 3, which equals obviously the opposite of sigma 3, sigma 1. When I say this equals the opposite, I'm not saying in particular for this group, obviously. It's by definition, this has to be antisymmetric for the Lie group to be a group. In fact, I should have gone back. When I said a while ago that we needed to show this was closed, yeah, it's true we need to show it's closed, but it also must be axiomatic that sigma I equals 0. And by bilinearity, using the fact that sigma is bilinear, you can say sigma I, sigma j must equal sigma j, sigma I with an opposite sign, right? So that's another thing you have to prove. But we know for our bracket operation, we know that that's satisfied. So I didn't really need to check it because it's satisfied no matter what for our bracket operation, the bracket operation we have, by the nature of matrix multiplication. But in order to formally be a Lie algebra, you have to satisfy this tricky thing down here, the Jacobi identity. I don't want to call it a tricky thing, I'll just name it. It's the Jacobi identity. It has to be closed under this bracket operation, which we've just demonstrated that it was. And it also has to have this property here, sigma I equals 0, which is equivalent to antisymmetry in the bracket operation. Okay, anyway, so now we've got these two, so I'll put them aside also. Okay, and then the third thing we learned about was these two guys, and those are our structure constants for this, and we learned about that from these commutators, these brackets. Okay, so now what we also know about some additional zeros. Basically, everything that's not one of these is zero, which if you look at it, it's anything where a number is repeated, right? So if I had any pair where I see 3, 3, or 2, 2, or if I see more than one of any digit, any of the numbers 1, 2, or 3, it's a 0. And if I see a 0 anywhere, right, it's going to be 0. So there's a very limited number of structure constants that are not 0. Okay, but I can look at these and I can actually I can tighten this up a little bit semantically using the permutation symbol. So the permutation symbol is epsilon. Let's see, I guess it's ijk, and epsilon ijk is going to equal 1 if ij and k are a cyclic permutation of ij and k, and it'll be -1 if ijk is not a cyclic combination of ij and k. So I guess the way to think about it is E1, 2, 3 equals 1. So does epsilon 2, 3, 1 and epsilon 3, 1, 2. Those all equal 1. But then epsilon 2, 1, 3, epsilon 1, 3, 2, and epsilon 3, 2, 1, all of those guys equal -1. And if it's not a permutation, right, if it's epsilon 1, 1, 1 or epsilon 1, 2, 2, if it's not a permutation of 1, 2, 3, then it always equals 0, right? So that's the definition of that thing. And we can kind of use that to tighten up if we wanted to, if we were so inclined that we wanted just to write this down as Cijk, like that. If we wanted to write it Cijk, well then, let's see. What would it look like? I think it would be epsilon ijk times 2I, where obviously this is the square root of -1, and that's just an index, right? Okay, that goes without saying, I guess. So, this is a pretty easy way of writing our structure constants, right? And therefore, what we can say now, and let me erase some stuff here, I can write sigma I, comma, sigma j, right, equals, well, it equals Cijk sigma k by definition, right? That's what the structure constants mean. But now I can substitute that with epsilon I j k times sigma k, where now, because of the nature of the permutation symbol, I'm summing over these down indices. So just to be clear, I will write summation over k like that. So there you have it. Oops. Wait a minute. I'm missing, obviously, the 2i part, right? I'm missing that. Let me fix that, right? So this is supposed to be 2i sigma k. I guess the way you should really think of this is epsilon I j 1 times 2i plus epsilon I j 2 times 2i. One second, almost. And then this would be sigma 2 plus epsilon I j 3 times 2I sigma 3. And this is sigma 1 here, where I left off the epsilon I j 0 because we know those are all 0. So that takes care of this issue of the sum. It really is summed up and down. We just have to say that this upper indexed object equals this number, and then just execute the multiplication. So by doing the symbolic substitution, we lose the up-down structure, because you don't ever really want to write this permutation symbol like that. You don't want to do that. It's just not done. Okay. All right. So we're almost there. Let's sum what we've done up already one more time and see if we can make things even simpler. Well, so to make things simpler, I guess it really comes down to this 2i here, right? The 2i, wouldn't it be nice if it wasn't even in there, right? If it was just epsilon I j k. The point is when you're dealing with, remember, we've got this vector space G, this algebra, which is a vector space also, and we have, what we've decided that we've got sigma 0, sigma 1, sigma 2, and sigma 3 as the basis vectors. But we could change it. As long as we find 4 linearly independent basis vectors, we don't need to stick with those. So why don't we just change those basis vectors to somehow absorb that? And that's exactly what is done. So the basis vector x0, well here, the basis vector xi will be defined as I over 2 sigma I. We're obviously, well, right. I don't want to have to say the obvious that I is the square root of negative 1 in one place and it's an index on another. So we'll say x mu sigma mu, like that. So if I did that, right, then I would get an I over 2 here. Well, first of all, what would actually happen? Say we went back into here and we put, I over 2 in front of the sigma. Well, I would end up with an I squared over 4, right? Everywhere would, where'd I go? I'd end up with, so there'd be an I over 2 here. So the whole thing would be multiplied by I squared over 4, which would have flowed all the way to, where? It would have flowed to there, and then it would have flowed to, I guess this would have been an I cubed over 4, and I cubed is minus I, so that would become a plus I, then the 4, then this would have become a 1/2, so this would have equaled I over 2 sigma 2, which would have been x2, right? Because we're defining x2 is defined as I over 2 sigma 2. Phew. So what we would have been able to say in the end, if we had switched all the sigmas with x's, is this would have ended up equaling x2, and we would have written x1, x3 equals x2. Is that right? You see, I know something's wrong because it's 1, 3, 2, and that's an odd permutation, so I'm expecting a negative sign. So let's see where I messed up. Oh, no. I didn't actually mess up. No, I just need to be bold and eat my minus sign, earn my minus sign. So what we do is now the structure coefficient C13 in this new basis becomes minus 1, right? So that's kind of cool. And then this becomes plus 1. And if you do this for everything, what you end up with is back here, you end up with basically everything is the same except the final answer ends up being minus epsilon I, j, k, right? So C, I, j, k is minus epsilon I, j, k, and that's in the xi basis, where this, I like to keep in black, is in the sigma I basis, right? So that's why we will define the generators of the group this way. And you'll see that it's done in Gilmore and it's done in almost... Now, in most physics books, there's a problem with I, right? So I haven't gone into that fact, but ultimately, if you look back at the exponential map, in physics books, you see it written this way, and in math books, you see it written this way, where x is some generator from the algebra. The physicists, for some reason, we tend to introduce this I. I'll talk about that in more detail later to kind of get it clear. But you remember, right, we would have the momentum operator, right, is I, P, wait a minute. The momentum operator was I partial by x, right? So you have this I think there's a minus sign there too. So but the point is there's these introductions of I between physicists and mathematicians. It's totally conventional. But I'll make it clear in an upcoming lecture where I just deal with the convention question. But the point I'm trying to make is, for our mathematical sense, just changing the basis by using these basis vectors just cleans up the structure constant. So when you see, we're going to use these basis vectors, understand the goal. The goal is just to clean up the structure constants. And you still got a -1 in there, so I don't know how much cleaner -1 is from 2i. I don't know. I like 2i. I don't know if I care. But evidently, Gilmore says, this is the clean version. We're going to use this for our structure constants. Okay, so that explains, so what have we done? We've talked about the structure constants. We explained what they were, and we did we calculated them for an algebra where we were given the assumed algebra. I guess for the last slide, what I'll do is, why don't we have a look at this? I haven't talked about why this is important in a Lie algebra, but we'll get back to it. But let's just say a Lie algebra, this must be satisfied. It must be satisfied. So let's check. Okay, so this is the Jacobi, the Jacobi identity is that equaling 0, what I've just written down equaling 0. So let's just figure out these things. This guy here, well, first of all, let me just change this all to x's, because x's is our thing now. Clearly, if it works with these by linearity, it's going to work with these as long as they share the same structure constants. So let's do the calculation here. So the first thing I'll do is I'll substitute for these guys, right? Let's see what happens. So I just substitute this using the structure coefficients. So I know that for x, it's nice and easy. 2, 3, I need this permutation symbol. So the only one that's going to survive is 2, 3, 1, because all the others are 0. By the definition of the permutation symbol, I got the negative sign. And so 2, 3, well, it's 1, x1. Well, I don't even need to finish this, because what's that going to be? That's going to be by linearity, x2, 3, 1, x1, x1, which is going to equal 0. And you're going to see this is going to happen each time, right? This is going to pull out the permutation 3, 1, 2, which will drop out, but leave an x2 behind, which is x2 commuting with x2, which is 0. Because remember, by definition, in order to be a Lie algebra, the bracket has to be 0. And of course, our bracket is definitely 0. Or the bracket of a member of the Lie algebra with itself must be 0. So this is going to be a 0, that's going to be 0, and that's going to be 0 independently. And, okay, so it satisfies the Jacobi identity. All right, and that is enough for today. This was actually a pretty easy lecture, I guess. The key point is understanding this, that the structure constants really are a statement. The fact that structure constants exist the way they do is simply a statement of the closure of the binary operation that defines the algebra. The fact that this is closed means you have to have something like the structure constants out there. And the structure constants tell you, A, that it's closed, and B, it's a reflection of the fact that if you know this bilinear product for a basis, you know it for everything, right? So that's the big takeaway. We also played around with changing the basis elements purely for convenience, right? Purely for convenience, just to get rid of this 2i, I guess introducing this minus sign. I wonder if we could have gotten rid of the minus sign. I think if we had made the definition, have a minus sign here, it seems to me that we could have gotten rid of the minus sign altogether. But then these xi's wouldn't look like the famous Pauli matrices, because right now the xi's look like, for example, x0 is I over 2, 0, 0, which you can quickly kind of work out in your head as just 1/2 I over I, and you can kind of see it as, I don't know, it seems to me like, I don't know why we didn't put a minus sign there. Whatever, the point is that that's a non-substantive change, but it is one of those things that kind of adds up as a sort of a learning burden of like convention on convention. The point is once you exhale and realize, hey, look, all they're trying to do is make these structure constants sort of simple and sweet. And in this particular algebra, we've got the benefit of using this permutation symbol, which is not typical, but for this algebra, which is a very important algebra, it is. So since it shows up at all, let's make it all by itself, except the minus sign. I don't know. Okay, so the next lecture, what we'll do is we'll take our example algebra and we'll work back and develop the group. We'll go back to the group concept and we'll see how we exponentiate this to get the group. Okay, see you next time.